have Professor Akito Futaki from Tsinghua University to talk about uncoupled Kähler-Einstein metric. Let's welcome.
Thank you for the introduction. Talk about coupled Kähler-Einstein matrix, which is a natural extension of Kähler-Einstein matrix. X is a compact Kähler manifold, and G is the Kähler metric, and Kähler form is a one form to satisfy the Kähler condition. So it defines a homology class called Kähler class. Rich curvature is given in the Kähler case, in this form. And Ricci form, this is also a type 1 form with coefficient rich curvature. So it's written like minus I dd bar, del bar of log determinant of GK bar. Calabi's problem is to find a Kähler-Einstein metric satisfying this equation. These are Ricci is equal to constant times Gij bar, but this constant can be normalized so that -1, 0, or 1. And this amounts to solving the complex Monge equation. This G is a given metric. F is determined from G, so these are known functions. And the Chang-Wei theory, which first Chang class is represented by Ricci over 2 pi. So if there is a solution, if there is a Kähler-Einstein metric, then natural conditions first Chang class negative or zero or positive. And negative case, there is a solution, Kähler-Einstein metric by Yao and Orban. And zero case, also solution exists. It's due to Yao. So the solution is called Calabi-Yau metric, and the X is, in this case, Calabi-Yau manifold. Positive case, it's called X. In this case, X is called a Fano manifold. There have been known obstructions, for example, Matsushima and myself, but there are other obstructions. In 2015, Chen, Donaldson, Sun, and Tian proved on Fano manifolds there exists a Kähler-Einstein metric. The existence of Kähler-Einstein metric is equivalent to a notion called K polystability, and I'll define later. And K stability is Donaldson-Futaki invariant of the infinite dimension GIT weight. So I'm not modest, so I call it Futaki invariant. Sorry. And then, so this is the topic that I want to discuss today. And K tuple of Kähler-Einstein matrix omega 1, omega k on the compact Kähler manifold X is called coupled Kähler. Einstein missing. Coupled Kähler-Einstein matrix if it satisfies this equation. So Ricci, these have the same Ricci curvature, and it is equal to the sum of omega i's from 1 to k. So they are all equal to this. This is the equation. And again, lambda can be normalized -1, 0, or 1. This was introduced by Hartgren and Nystrom. So let's examine the 3 cases. If lambda is 0, then this term is 0. So these are all Ricci flat metric. Necessary condition is first Chang plus 0. In this case, the solution exists by Yau solution to Calabi conjecture. So there's nothing new in this case. So the problem is when lambda negative or one, negative, positive, and the existence so these are necessary conditions, and how to learn and with Newton prove the existence of the solution for lambda negative, lambda minus 1, under the condition C1 negative, extending Yao and Oban. So this case can be extended. And also they studied the case of lambda equals to 1 under the Fano condition, including attempt to extend chain Ransom Sun and Tian, but they didn't give an absolute answer characterizing the existence by stability condition. More recently, Fujita Hashimoto gave an equivalent uniformly, actually this is the stability characterization of the existence of coupled Kähler-Einstein matrix in the positive case. So this talk is about my report, what I understood from this paper. So this work heavily depends on the earlier works in the case of Kähler-Einstein metric, so K equals to 1 case. So I want to give a brief history about the solution in the Fano case. So this is a history up to Chen Sun Tian to this Fujita Hashimoto. So this case, so K equals to 1 case, that is uncoupled case, is just positive Kähler-Einstein matrix. After Chen Sun and Tian, there are other alternate proofs by Data Sekirihidi and Chen Sun Wang. This is a cone angle argument, and this is a continuity method. It is Ricci flow proof. They all use Gromov-Hausdorff convergence, but another proof used variational proof without using Gromov-Hausdorff convergence was given by Baumann, Luxon, Johnson under the condition of uniform K stability, and Baumann, Luxon, Johnson case, the automorphic group is discrete. This is basically a complex analysis proof, like the potential theoretic proof. Yes, was talked by Baumann, Davas. For non-discrete automorphic group case, Chi Li showed the existence under condition of G uniform stability. So in this case, G is non-trivial automorphism group, a subgroup of automorphic group. The work of Du Xiu Yuan showed that when G contains the maximal torus, this G uniform stability is equivalent to K polystability. So combining all of this, the existence is equivalent to K polystability. This is another proof. So recently, Fujita Hashimoto extended the work of Chi Li, and Yu Yuan to positive coupled Kähler-Einstein matrix. So this talk is a survey of the work of Fujita Hashimoto, including my joint work with Yin Zhang. Also, I should mention that this Baumann, Luxon, Li, and Fujita Hashimoto rely on the work of Davas Rubinstein's work about this existence. But our formulation is more algebraic. So this is what I want to talk. So the general idea, this was also discussed yesterday in Davos talk. General idea on the finite dimensional variational problem. There is a unique critical point if the functional is strictly convex and proper. Strictly convex and proper, there's a unique critical point. So in the Kähler-Einstein problem case, it sets a variational problem for functionals called a Mabuchi functional or dim functional on the space of Kähler matrix. So space of Kähler matrix are infinite dimensional, so it's not so simple in the finite dimensional case. And then to describe properness, Aubin's J function has been used, or Darvas D1 distance yesterday appeared, has been used to play the role of the distance on the space of Kähler matrix. This uniform stability is a way to describe the properness by means of the infinitesimal behaviors at the infinity of the function of Mabuchi D1 Aubin's J using the limit of this ratio is a sort of derivative at infinity. This is called slope or non-Archimedean function in the terminology of Bergson, Hisamoto, Johnson, and for a function of f along a ray in the space of Kähler matrix, often geodesic ray. And then we need a definition of a test configuration. A test configuration describe the problem, the condition in terms of algebraic geometry, but this is a sort of replacement of a ray. So I want to explain it. So given a ample line bundle L over projective variety, ample means the first chunk is positive. So the class, the homology class of C1L can be considered the space of Kähler matrix or Kähler forms. And then we assign normal polarized variety Kähler with the following properties. There's a sister action Cal-X lifting to Cal-L. There is a flat sister equivalent morphism from Cal-X to P1 projective line with the standard C1 action. So this X has a sister action, P1 has a natural action. So the pi is a equivariant. Flat means something I explain later. And then P1 such that outside zero, this XL is equivalent to isomorphic to this Roman X times C star plus infinity, adding this infinity and pullback of LR with the trivial action on the first factor X. So in this case, this is just a product with this line bundle, sort of. So just X times C adding infinity, C star adding infinity times this product. So equivalent isomorphic, just twisting the group action. This is just a product. So the problem. So I would say this exponent R appears here. This R, and so something special happens over the central fiber, over the fiber over zero. So here I remove zero. So outside zero, nothing interesting, but something interesting happens over zero. And zero is the fixed point of the sister action. So the fiber over 0 is preserved by the sister action. So this x, but x0 could be either sister equivariant degeneration of x, possibly singular. So this will be something interesting. And so this almost means that this flat means there's a so each fiber is just x and L. So we have this flat means each fiber, so fiber can be embedded in the higher projective space in the equivariant way. So outside 0 is just a sort of product, but over 0, x may degenerate to a singular one. This is what this means. And the special one, when originally XL has a sister action, then outside infinity, we can consider a pair of cal X or cal A, which is isomorphic X L times C with diagonal sister action. Then this is a this satisfies the condition test configuration, and this is called the product configuration. So the central fiber is this original XL with the given sister action. And in comparison with this variational problem, this S corresponds to minus log of t. When t goes to 0, this S goes to infinity. It is well known that a test configuration is associated with a weak geodesic ray in the space of Kähler forms, C1L. So the metric behavior near the central fiber describe the behavior of the slope of Mabuchi or Dean function as S goes to infinity. This is the relation between sort of the program, this program itself, and algebra geometry and analysis. So I didn't prepare exact form of Mabuchi function or a Dean function. So I need to define invariant associated to test configurations. So I introduced how to learn with instant coupled Donaldson-Futaki invariant. Take ample Q line bundles L1, Lk, satisfied minus Kx is the Q equivalent to the sum of L1, Lk. So these Lis include, the first chunk class include the Kähler forms. The sum of Kähler forms replace the first chunk class, rich curvature. So the sum of omega I should represent minus Kx. So in this situation, last time in the Kähler-Einstein case, we consider given XL, we give test configuration. So in this case, how to learn Newton used so for each x on Li, they consider cal x, cal Li as a sort of coupled test configuration. And I emphasize that this this cal chi is the same for each Li in Hawking-Easton case. And then Donaldson-Futaki invariant is expressed in this in the form of intersection form. So this Li, this is an intersection of n+1 divisors in the space of cal x, but this lower this kx is a divisor on x, Roman x. So these are intersection on x, and these are intersection of cal x. This originally was defined in a differential geometric way, but later, so soon I realized that this can be interpreted as an equivalent cohomology. So in the equivalent cohomology, this is already in this case, when k is equal to 1 case. And later, Xiaowei-Wang and Odaka found that the same formula applies for even for degenerate case. So now this invariant express, this expression is used as a definition. I'll show later differential geometric form. But now I define this in this case. So when k equals to 1 case, this is a standard definition, but this coupled case, they define in this way. For each Li, take this computation and take the sum in this way. And then so for k equal 1 case, Kähler-Einstein case, Chan-Donaldson defined that this x with minus kx is k polystable if this invariant is non-negative for any test configurations, and the equality holds only for product configurations. The product configuration case is my original definition of that invariant, the character. Then for k general case, when we Nilsson define this k-tube of line bundles, such like this, is k polystable if their Donaldson-Futaki invariant is non-negative for any test configurations, and the equality only holds for product configuration. And then they show that the existence implies k prosperity extension of Baumann, and the uniqueness modular connecting group actions, extension Bandor-Mabuchi of Baumann-Berntsson. Their proof use Baumann-Berntsson's argument. And then following Baumann, Fujita Hashimoto defined Ding invariant using different test total space of test completion. So I said in their case, they use the same chi, but Fujita Hashimoto use different carrying psi. And then k equals 1 case, uncoupled case, Kähler-Einstein case, Baumann defined Ding invariant. Baumann began to use Ding function because Ding function is better to use in Kähler-Einstein case. And Ding invariant is a slope of Ding function. I will not write down Ding function, but I just define Ding invariant. Is defined by in this form. So the first time expressed by intersection, but the log canonical threshold appears. This appeared in the definition of Ding function. This is a invariant in birational geometry. So this suggests that the problem should be closely related to birational geometry. And so this divisor is supported on the central fiber, which is Q linearly equivalent to L minus K chi over P1. And this is a soup of this to be log canonical. Log canonical means there's so if mu is a proper binomial map, so like Hironaka's resolution, Y regular, and E is a divisor of Y. Such E is called divisor over X. It's upstairs. And then the coefficient of this divisor, coefficient, this divisor has coefficient of E as minus bigger than or equal to -1. This invariant can be interpreted as follows. This divisor defines a measure on the space on chi, and this measures whether that measure has finite measure. So this is invariant variation geometry, but it's closely related to measure theory. Or so in that way, this appears in the to calculate this dim slope of dim function. This was observed by Bauman. And then for occasional case, Fujita Hashimoto considered this sum of test configuration, and T is the maximal torus in the reduced automorphic group. Reduced automorphic in this Kähler-Einstein case, this is just a automorphic group. And then for I from 1 to K, take T equivalent test configurations and take a sufficiently divisible Ri and set Ri for each I to be the section ring. And then the section ring can be expressed in this way. This Roman Ri is H0 Roman X and L. This is a filtration of this XL obtained by image of the restriction of the lambda weight space to the fiber over 1. The fiber over 1 is the same as X and ML. So this gives a filtration of ML. This form, giving this kind of filtration is required to giving the test configuration. It's well known. And then take a C star times T equivalent common resolution sigma I Z over chi I. Chi i's are different for each I, but we take a common resolution Z normal sigma I isomorphism over C outside 0. And then we define Cal Rm, which is the image of this tensor product to this space, and this space is known to be injective, and then this is subalgebra of this, and this is finite generated, and induces a T equivalent test configuration X, Cal X, Cal L, and this is argued by Buxon Samoto and Samoto Johnson and Buxon Samoto Johnson and Fujita and Hashimoto call this XL sum test configuration. So they use different XI, so they wanted to take sum of xi, li in this form to define Dean functional. So they define coupled Dean functional as a Dean of this sum test relation. This Dean invariant is this in this Excel, and then at some this intersection. So this is the invariant to describe uniform stability, but we need to have also have a distance, slope of distance j function. This is for k equals 1 case. This is also known as that the slope of j function can be expressed as an intersection number in this form, and then the coupled j is the sum of this. And then we need to take care of the group action so that to describe the convergence, because when there's a non-compact group action, then the space of solution is non-compact, and it's difficult to show the convergence. So it's some operation to ensure convergence. This is the operation. So this is the algebra of T and Q in the Q point in the Lie algebra, and Z. For each Lie algebra element, we consider something called Z twist of test configuration. This is just a twist of the sister action by one parameter of Z. So we need this operation, and then we say the pair of LIs is T equivalently coupled Dean semi-stable if their Dean invariant is non-negative, and we say this K-tuple line bundles is T reduced uniform coupled Dean stable if there exists a positive real number epsilon such that Dean invariant is bigger than or equal to this slope of this distance function. So this describes the infinitesimal behavior of the function and the distance. This is the main result of Fujita and Hashimoto. This K uncoupled case, Kähler-Einstein case is due to CD. The TR be the maximum compact torus. So this complex algebraic torus is the complication with the torus. Then the following equivalent. First, X and Li's are T reduced uniformly Dean stable such as this equation, this equality. Second, this pair admits a TR invariant coupled Kähler-Einstein matrix. This means that the omega i's belongs to the first chunk of Li's and satisfies T torus invariant coupled Kähler-Einstein matrix. And third, this Xi has a vanishing coupled T Futaki character and the Futaki invariant, and delta invariant reduced T reduced delta invariant bigger than 1. I define this later. And this is something called delta invariant or stability threshold. I'll do later. So let's explain what this couple character. This is the original form. K equal 1 is the original form I defined. And first chunk class is the sum of cohomology classes. These are Kähler classes of omega i's. So if you pick omega i's and li's, for each I, which form represents the first chunk class, the sum also represents the first chunk class. So the difference should be I del bar of some smooth function Fy. So this equation shows that del bar of this form is are all equal. This equation shows. So they are equal absolute to constant. So adding some constant Fy, we may assume they are all equal. So we consider this as a volume form. So, and then let Z be a holomorphic vector field. Then Fano manifold is simply connected. And then inner product of Z to omega I, this is D del bar, or this is 0. It has to be a del bar of 0 form, so it's a smooth function. So I put this square root minus 1 with I. When Z is a killing vector field, holomorphic killing vector field, this is just a Hamiltonian function, the killing vector field. Killing vector field is a Hamiltonian vector field, and Ui is a Hamiltonian function. So we can consider a moment map. Then we show that this D algebra expressed by set of K2 complex valued functions satisfying these equations. The gradient are all the same, which this is a from a vector field, and it satisfies this equation. These satisfy this equation. And then we can, as a corollary of this, is that if X admits a coupled Kähler-Einstein matrix, this Hx is reductive. This is because I don't have much time, so I skip this. And then this is also expressed as the space of this K2 sum of functions, such as this normalization constant. And this normalization constant is the same as saying that moment polytopes of Li's are equal to Minkowski sum is equal to the moment polytope of the canonical line bundle minus anti-canonical line bundle. And the Futaki character is defined in this way. And this is independent shear metric. And if there is a Kähler-Einstein metric, this invariant is 0. Let's check if there is a Kähler-Einstein metric, this invariant is 0. It's because in that case, if there is a solution, Fy or 0, so these are all equal. Omega 1 to the n, omega 2, k to the n are all equal to dV. And then these are all the same, omega i's are all the same. So the sum becomes just a sum of integral over dV. And then this normalization condition means the sum is 0. As in this case, that is 0. So this is how we see this 0. Then let's see what delta invariant of stability threshold called valuative criterion due to Fujita and Lee. So again, we consider a divisor over x. This means that mu is a proper variation and y is regular and e is a divisor in y. And then we define log discrepancy as in this way. And then expected vanishing order is defined in this way. This something weird to express variation invariant in the integral form. It's originally defined this in algebraic way, but by elementary calculus, so this is the same as this integral. This is what this means. And then beta invariant is ax minus ax se minus se, defined for divisors over x. And then Lee and Shu, Chen and Shu, proved this. To test K stability over KLT or smooth funnel variety, it is sufficient to consider special test configuration. Well, the central fiber is KLT, normal, integral, so reducible. So this is enough to consider this. This is the original definition by Tian, but Tian's definition was criticized because derivation is not normal in general, but this justifies Tian's definition. It's enough to assume these special properties. And then any normal test configuration in this is GM, this is a sister equivalent birational morphism, birational map from this test configuration to this product. So we have isomorphism of function field. And then if V is a variation on this space, so for this space, then we denote by RV its restriction to Kx. For special test configuration, there's a divisor over x satisfying this equation. This means that the special test configuration central fiber is integral, reduced, irreducible, so we consider the order along E0, just and then so this is a variation x, and then capital X, and then restrict to k of Roman x, and this it is known that this one is also a divisorial divisorial variation. So we can find the divisor with I or E over X with this property. So this is well known. And then a fact is that if X minus, if this test configuration has integral central fiber, then Donaldson-Futaki invariant is expressed in this way, this beta invariant in this for special test configuration example. And then, so this is exactly the Futaki invariant in the special case. So I'm motivated by this. It was shown by Fujita Lee that if X is K semi-stable, this invariant is non-negative for all divisors U over X. So this is only the case of special test configuration. Still, in general case, still this is true. This is a nice result. And then Bloom-Siu showed that if X is K stable, X case stable if and only if this beta invariance is strictly positive for all divisors over X. And then Fujita, Odaka, Bloom, Johnson defined a delta invariant or stability threshold as inf over E prime divisors over X of this ratio. But Fujita Odaka used M basis type divisors, but Johnson found this is also true. Then K semi-stable if and only if delta is bigger than 1 or equal to 1. K stable, delta is bigger than 1. This is just the same as, this is the same as this. And then, so what Fujita Hashimoto extended, this is Kähler-Einstein case, extended delta invariant in this way. So I'll not define the exact this technical definitions, just a quotient of AX over the sum of SLI. So this, as I said, we have to take care of something difficult to treat when there's a group action. This is something. This V is a variation, divisory variation, and Z again twist by almost vector field. So I will not give a detail of this operation, but the idea is exactly the same as before. So Fujita Hashimoto proved stability implies existence. This is a difficult part and relies on the work of Davos Rubinstein, as I said before, together with some analysis of Halpern, Yislim, and Chidi. More recently, Kuei-Jan introduced analytic delta invariant related to Mozart-Schrödinger inequality and showed delta n is analytic delta invariant equals to delta and gave a new proof of Yao-Donaldson conjecture, very closer to original approach using Mozart-Schrödinger inequality, this kind of to solving this kind of Monod equation. So maybe a bit too early, but I want to finish.
For the interesting, exciting talk, any question for Professor Futaki?
So what was the motivation of the authors for studying couple Kähler-Einstein?
What is the motivation?
Yes, why they wanted to generalize that and study?
Realize what?
No, why they wanted to generalize?
Motivation coupled case. I don't know. Actually, it's due to Halpern and interest. To me, it's interesting because much has been done for Kähler-Einstein case and this coupled case. It's quite new, so should be interesting. So this. Actually, I don't know. Well, it's just maybe just an idea. No other field or no other motivation.
You can define it in great generality. I'm not sure. There may be coupled Kähler-Einstein metrics when there are no Kähler-Einstein metrics. So there are still some sort of canonical metrics that you can associate in a more general situation. Maybe that's the motivation. I will not swear to it.
Maybe, yeah, maybe, the motivation, it has more cases that can have canonical metrics. That could be the motivation. Huh? No example. Not. There is an example. So Hartman and Newton gave an example. In the toric case, there is an example where the original Futaki invariant is non-zero, but coupled one has a zero. It depends on the combination of omega i's. So choosing a good combination, the coupled Futaki invariant vanishes. In toric case, vanishing of Futaki invariant always assure the existence. So in that case, no Kähler-Einstein metric, there is a coupled Kähler-Einstein metric. There is such a toric case. It was due to Hartman. We need to.
Existence of coupled Kähler-Einstein metrics implies semi-stability, slope semi-stability. Is that known?
Coupled Kähler-Einstein metrics, yes, that's yes, it's
And then do you get interesting new Chern class inequalities in this case?
chance inequalities probably that would be possible. So no one has that yet.
Any other question for Professor Futaki? Okay, if not, then let's thank Professor Futaki again.